In this video, we're going to talk about the second topic of Chapter 9, heat and work. In the previous video, regarding the first topic, we talked about the energy can be transferred between a system and its surroundings. Okay, the energy can be transferred between the two. And we know there are two types of energy, kinetic energy and potential energy. So if you want to be more specific, you would consider the kinetic energy and potential energy separately. K represents kinetic energy, P represents potential energy. All right, and if you want to be even more specific, okay, you are going to consider heat as one type of kinetic energy and work as one type of potential energy. What does that mean? Well, remember, heat is related to the temperature, right? And temperature, higher temperature, the molecules will move faster. So it's about the speed, motion, right? Higher speed, higher kinetic energy. So that's why heat is one type of kinetic energy. Work is about the positions. For instance, the position of the piston in the engine. Therefore, it's about the positions of an object. Therefore, work is one type of potential energy. So heat and work are the two most common energies that we're going to deal with in science, okay, and be more specific in chemistry. And most of the time, we're going to focus on the system, okay? So in other words, if you are considering system only, then you are going to consider energy or the heat. We use Q to represent heat and W to represent work. Okay, so when you consider the energy change of the system, then you have to consider both Q and W, both heat and work. All right, let's take a look at heat first. How do we calculate heat? There are two equations. Well, the first one is Q equals to C times delta T. The second equation is Q equals to M times CS times delta T. Okay, for both equations, delta T is the temperature change that equals to T final minus T initial. TF is the final temperature, TI is the initial temperature. Now, for the top equation, the C is the heat capacity. Unit is joule per degree Celsius. For the bottom equation, M is the mass. CS is the specific heat capacity. All right, so which equation should we use? Well, you take a look at the unit of C and CS. C unit is joule per degree Celsius. Okay. Well, by the way, the specific heat capacity, the unit is joule per gram per degree Celsius. Okay, so what I'm trying to say here is C and CS can help us understand which equation we should use. For C, as you can see, unit is joule per degree Celsius. Mass is not involved. But for CS, specific heat capacity, mass is involved. Therefore, in the question or in a system, if mass is not involved, then you use the top equation. If mass is involved, you use bottom equation. Okay. On your right side here, this is a table about the specific capacity data of some common substances. Okay. While for elements, you can see that they have specific heat capacity, compounds, and materials. Remember that specific heat capacity is an intrinsic property of those substances. Okay, it's just associated with one particular substance. Okay, it's like a density. All right, density. No matter where you measure the density, it remains as a constant. Same thing for the specific heat capacity. That because they are constants, they will be given in your test. Okay. Now let's take a look at this problem. It can demonstrate how we use this equation to do the calculation regarding heat. How much heat is required to warm 0.69 kilogram of water from 35 degrees Celsius to 120 degrees Celsius? Well, if you do a quick analysis, you realize that mass is involved in this equation. Therefore, we need to use the bottom equation. Okay, now let's plug the data in this equation. Mass is 0.69 kilogram, while the unit of the specific heat capacity of water is joule per gram per degree Celsius. Therefore, I would like to convert kilogram to gram. Okay, so 0.69 kilogram times 1 kilogram at the bottom and 1000 gram on top, and then CS water right here times 4.18 joule per gram per degree Celsius. Now the next thing is delta T. Well, delta T equals to T final minus T initial. Well, as the question describes here, temperature increases from 35 to 120. So 120 is T final, 35 is T initial. Okay, so it's going to be 120 degrees Celsius minus 35.0 degrees Celsius. All right, calculation itself is quite easy. You just need to know which equation you need and plug that number in the equation carefully. And if you do the calculation, then it will be a quite large number, 24, 51, 57 joule. All right, and how many significant figures? Well, you have 2 here, so apparently we should have 2 significant figures in the final answer. In this case, we do have to use scientific notation. That will be 2.5 times 10 to the 5th joule. Okay, so this is how we use this equation. We will discuss how we use this equation in one of the other practice problems, okay, in a moment. Now, this is how we calculate the heat. Let's take a look at this problem. Okay, a block of iron has an initial temperature of 85.3 degrees Celsius. The iron is dropped in the beaker with 45.6 grams of water at 23.4 degrees Celsius. In other words, metal is hot and water is cold. When the system reaches the thermal equilibrium, the final temperature is 26.9 degrees Celsius. Okay, when you first drop the metal into water, apparently the energy, the heat, will be transferred from metal to water, and the temperature of metal will drop, temperature of water will increase. But after a certain amount of time, both of the metal and water will reach the same temperature right here. So the heat transfer will stop at that moment. Okay, so that's what the thermal equilibrium means. What is the mass of the iron? Specific heat capacity is given. Specific heat capacity of water is also given. Well, you can see that mass is involved in this problem. Therefore, we should use the specific heat capacity to solve the problem. In other words, we should use Q equals to M times CS times delta T for this particular problem. Now, if you happen to remember between the system and its surroundings, okay, energy can be transferred. And we know that if the system, for this particular situation, energy is going from system to its surroundings. And in the first topic, we talked about this situation when the energy is transferred from system to surroundings, delta E system would be negative because system is losing energy. But for delta E surroundings will be positive in this case. Okay. Well, please remember the absolute value of those delta E surrounding and delta E system would be the same, but they have the opposite sign. Okay. Same situation for this hot metal and cold water. Q is the heat energy. How much energy released by metal will be absorbed completely by water. So the absolute value of the heat energy change of metal equals to the absolute value of the heat energy change of water. So that's why we have equal sign between the Q metal and negative Q water. But why do we have to have a negative sign right here? Well, let's go back to this part. One is negative, the other one is positive. So in order to let them equal to each other mathematically, you have to put a negative sign in front one of them. Okay, so that is how we set up this equation. So the negative sign can be in front of Q water, in front of Q metal. It doesn't matter. For this, traditionally we put the negative sign in front of Q water because water in this case it's surroundings. All right, so this equation will help us solve this problem. So we need to calculate Q water and then use this equation to solve the mass of iron in this particular case. Okay, so let's go ahead and get started. For Q iron, that should be M iron times CS of iron, 0.449 joule gram per degree Celsius, times the temperature change, delta T. Well, the initial temperature of iron is 85.3 degrees Celsius. Final temperature is 26.9 degrees Celsius. So T final, 26.9 degrees Celsius minus 85.3 degrees Celsius. All right, so this is a Q iron. And remember, we cannot calculate how much Q iron is because the mass of iron is unknown. All right, how about Q water? Q water, we use the same equation here, okay, equals to the mass of water, 45.6 gram, times the specific heat capacity of water, 4.18 joule per gram per degree Celsius, times the final temperature minus initial temperature. Apparently, final temperature is 26.9 degrees Celsius minus initial temperature right here, okay, before you drop the hot iron, 23.4 degrees Celsius. And this can be calculated, all right? So if you do the calculation, it will give you 67.128 joule. And we are supposed to have 3 significant figures. Okay, so according to what we just discussed here, you have, I would put this one step 1, step 2, because Q iron equals to negative Q water. Okay, so that will give me M iron times 0.449 joule per gram per degree Celsius times, well, if you do the calculation of this part, okay, it will give you negative 58.4 degrees Celsius equals to negative Q water. We did the calculation here. Okay, so that should be 667.128 joule. All right. Now, as you notice, the M iron can be calculated because you just need to divide the two sides by this part. All right. Let's go ahead. So the M iron equals to negative 667.128 joule divided by 0.449 joule per gram per degree Celsius times negative 58.4 degrees Celsius. All right. Now, if you do the calculation, you'll get the final answer of iron. The mass of iron is 25.4 gram. All right. So this is the calculation. So what can we learn from this example? First, we learned how we use this equation again. And the second thing is consider the delta E surroundings and delta E system. Okay, and they have the opposite sign. One is negative, the other one is positive. Okay, so that's why we have this kind of setup for us to find out the mass of iron. All right, now let's take a look at work. We discussed how we calculate heat. Let's take a look at how we calculate work. Well, let's take a look at this picture first. With this picture, it's sort of like a cylinder with a piston. Okay, well, the work that can be done by this piston is related to the position of the piston. This is the initial state of the cylinder with its piston, and this is the final state of the cylinder and its piston. As you can see that the volume in this space is expanding, okay, from here to here. All right, so that means that the piston is moving up. All right, so the delta V, the volume change, is related to the position of the piston. Okay, so well, if this piston is one of the cylinders in car engine, for instance, if the piston is moving upward, it's driving. You can drive your car. That means this piston is doing its work. Okay, so that is why we said that work is one type of potential energy because it's related to the position of an object. How do we calculate work in this case? Well, here is the equation for us to do the calculation. W, remember W is work, equals to negative P times delta V. P is the pressure. All right, and the unit should be ATM. Okay, atmospheric pressure. Delta V is the volume change. Delta V is equals to VF minus VI. VF is the final volume. VI is the initial volume. It's like final volume, initial volume. All right. Now, if you take a look at the unit for W, that's going to be unit of the W. That's going to be ATM and liter. Okay. For instance, if you are talking about the volume change of liter, then that's going to be ATM times the liter. Well, we know that when we talk about the unit of energy, we said that the two most common units for energy are calorie or joule, and it looks like from this equation, none of those two units, is involved. So, what should we do? Well, here is the unit conversion factor. Okay, so that's going to be 1 ATM times a liter equals to 101.3 joule. All right, this is a unit conversion factor to convert the work from ATM times liter to joule. All right, now you can see that we can connect the work to the unit of energy. All right, this is the this unit conversion factor will be given in your test. But let's use this example to demonstrate. Okay, a cylinder expands from 0.45 liter to 1.245 liter at 1.58 atm. How much work in joule is done? Well, again, car engine here, example here, you are expanding the volume inside this cylinder, so work is done by the system. All right, so it drives your car and move forward. So how do we solve this problem? Let's use this equation to do it. Well, the first step is W equals to negative 1.58, this is a P, times delta V. The final volume is 1.245 liter minus 0.485 liter. Okay, so in this case, equals to negative 1.20 liter times ATM. Now the second step is to convert the L or ATM times the liter. Okay, it doesn't matter, but I still want to be consistent, so it's going to be ATM times the liter. Okay, all right, now let's convert ATM liter to joule. So that's going to be negative 1.20 ATM times joule. Okay, we know that's 1 ATM times joule times liter is 101.3 joule. Okay, if you do the calculation, it will be negative 1.22 times 10 to the second joule. In order to keep the right significant figures, we need to use scientific notation in this case. Okay, well, pay attention to the negative sign here. Well, the W is negative, which means when this cylinder expands, this engine is doing work to its surroundings, which means car itself. Therefore, this car engine is losing energy. That's why it's negative. All right, so this is how we calculate work. Okay, let's take a look at the chemical reactions. As chemists, we do chemical reactions, and in order to make our reaction system simpler, okay, we will try to make system. When we do chemical reactions, we will do reactions in the system. We will design a system that can have minimum volume change. Okay, why do we do that? Let me explain it. Well, we know that delta E reaction, ideally or in theory, it should contain two parts: heat, energy, and work. All right, you should consider both when you perform a chemical reaction. But when in chemistry, we are always interested in the heat energy. Okay, so we want to design a system or reaction container, for instance. So this reaction container, the volume of this reaction container will not change during the chemical reaction system. Therefore, in this case, W would be 0. So we have a better focus in this case. Okay, so that means delta E reaction equals to Q only. Okay, and here this picture tells you this specialized container that we use for us to measure the heat energy associated with one particular reaction. Well, this is called bomb calorimeter. What happened here is this container is made by steel. Okay, before you start your reaction, you load your compound in this smaller container, and then put that in this larger container. And here, these wires, they are electricity to spark to spark the reaction, to let the reaction start. And you have a thermometer to measure the water temperature around this small container, and you have a stirrer here to make sure that the temperature is homogeneous through all of the water media. Okay, in this the bomb calorimeter. So as you can see that this bomb calorimeter is made of steel, so the volume of this and also this small container. So the volume will not change during the reaction. So by measuring the temperature change of water, we can identify how much of the heat is absorbed or released by this reaction. So we can better understand this reaction system. All right, let's take a look at this problem. You burn when 2.35 gram of ethanol burns in the bomb calorimeter. Here, this is the methanol burning. The temperature rises from 24.05 to 31.33. In other words, the water temperature rise. That means the reaction will release the energy to water, so that's why the water temperature increase. All right. Find the delta En for burning 1 mole of the ethanol. The heat capacity of the bomb calorimeter is this much. Again, this is the between the a system, reaction system, and its surroundings. Okay, here water and the bomb calorimeter is surroundings, and this small container with reaction inside is the system. Okay, so what happened here is, since the system is releasing energy, the energy released by this reaction is going to be absorbed by water completely. So based on the example we discussed in previously, the hot metal and cold water example, so you would have this relationship. Okay, so delta E reaction equals to Q reaction. Remember, we talked about right here, since this volume and this volume will not be changed. Therefore, you can ignore the W. So the delta E reaction equals to the heat energy of this reaction. And the heat energy of the reaction is the system here between the Q calorie. So this is the energy, heat energy that is associated with the surroundings. Okay, we call it calorimeter. So between this Q reaction and Q calorimeter, they are gonna have the absolute values will be the same, but they have the opposite sign. All right. So if we want to find out delta E reaction, then we need to find out how much the Q calorimeter is. Well, how do we calculate the Q calorimeter in this case? In our previous discussion, we know that there are two equations for us to follow. Q equals to C times delta T. Q equals to M times C S times delta T. We said that, the way to decide which equation you need is to see that you have the mass data for the substance with either specific heat capacity, or not. All right. So it looks like the heat capacity of the bomb calorimeter is given here, and no mass data is given for this the bomb calorimeter. Therefore, we need to use the top equation. Okay, so step 1, Q calorimeter equals to heat capacity 5.11 kilojoule degrees Celsius. You can keep the kilojoule in this particular case, okay, because it doesn't ask you for the unit for the delta E reaction, so you can use kilojoule, no doubt about that, times the delta T. Delta T is a T final minus T initial. T final right here, so that's going to be 31.33 degrees Celsius minus initial temperature 24.05 degrees Celsius. Okay, so that's going to be, if you do the calculation, it's going to be 37.2 kilojoule. All right, now Q calorimeter is done. So if you want to find out delta E reaction, well, you just need to use the equation we described here. So delta E reaction equals to negative 37.2 kilojoule. All right, now we are not done yet though. Remember, the question asks you to find out the delta E reaction for burning 1 mole of ethanol. In this particular calculation, we calculated delta E reaction by burning 2.35 gram of ethanol. All right, so in other words, I'll make a note here. Note this is associated with burning 2.35 gram of ethanol. Okay, I'll write the formula, C2H6O. And if you want to find out 1 mole burn the delta N for burning 1 mole of the ethanol, you need to do one more step. Okay, so you need to use this delta E reaction divided by the mole number of 2.35 gram of ethanol, and that will give you the final answer. So negative 37.2 kilojoule divided by convert 2.35 gram to the mole number of ethanol. Formula weight is given. It's 46.07 gram and 1 mole on top. Okay, and if you do calculation here, it will be 6.29, 3 significant figures, times 10 to the second kilojoule. All right, so this is this problem. We will do more practice when you come to class.